So today my topic is bringing AI machine learning into the 5G radio access network. I'm Jason from China Mobile Research Institute. Okay, first, as we all know, 5G is quite hot these days, and 5G is really becoming the reality. So here I would like to share the journey, the 5G journey from China Mobile perspective. So from 2019, we started some 5G technology tests in Beijing, Shanghai, Guangzhou, Ningbo, Suzhou. There are 7 sites per city. And after that, on 2017, we had some POC tests in 7 cities on 3.5 gigahertz. And after that, in 2018, we have 5 cities for more than 500 sites trial. So that at that time is the largest scale trial, and there are 12 cities for 9 service application demos. So after that, in 2019, that is next year, we have the pre-commercial trial on both the 2.6 gigahertz and 4.9 gigahertz large scale trial. And there are 3 or 5 cities had deployed the pre-commercial 5G network. And now 2020, the goal for this year is that we will have 250,000 5G base stations deployed in China Mobile's network. So 5G network is envisioned to change the world. It will not only provide a better user experience for the human-to-human communication, it is envisioned to also enable more innovation and intelligent industry. So next part, I would also like to share some trends of 5G network and some challenges here. So first, as we all know, there is rapid traffic growth these days, especially for the coronavirus spreading all around the world. So we are more reliant on the network. Another thing to mention, the 5G network is designed to satisfy diversified services. So we have the EMBB, the MMTC, and URLC. And with all this supported diversified services, the network becomes more complicated. We have a lot of different kinds of bands, and we have a lot of different kinds of base stations. We have the micro and indoor system. There will be quite complicated network. And in another way, the 5G network architecture also has some great paradigm shift. So from the core network, the 5G network becoming the service-based architecture, and we also enabled the hardware, software decoupling, the control plane, user plane decoupling. And in the radio access network, we had introduced the central unit and distributed unit split in the radio network. So the overall trend is that network is becoming more cloud-native, service-driven, and it will be driven by the orchestration and automation. So in all, a flexible, efficient, and scalable and programmable network is the key features for the 5G network. So another thing I want to mention is about the 5G network is not just for communication. We had a lot of data in our 5G network. So if you look at different domains, we have the business domain, and we have the maintenance domain, and we also had the operation domain. And each domain, we have different kinds of data. The data from the user, the data from the network, and also so for the data in the network, we have different kinds of data. For example, we have the measurement report of the network. We have the performance data. We have the alarm data. We have the resource usage data, and also a lot of signaling data in the network. So based on network, we believe the 5G network will be data-driven. That means the wireless big data and AI machine learning will play an important role in our network. So next page, we would like to share some opportunities and challenges we saw based on the flexible 5G network, and also a lot of data provided by the 5G network. So for the opportunities, there are some some great opportunities that we can see. So first is about internal, for the operators, internal digitalization, automation. The second is that it also opens up new revenue streams and business models and diversified opportunities for the operators. We are not only providing the network basis services, we can also provide some value added data services for our customers. Another thing to mention is that based on all this data, we can provide more personalized network experience for our end users. And regarding network operation efficiency, the data would help to reduce the manual work and improve the network energy efficiency and also the network resource efficiency. But we also face a lot of challenges here. So as I mentioned before, we have large amount of data in our network. So what data is really useful and where to collect and how to efficiently utilize this data. And the second part is about architecture. As we all know, the legacy networks are not designed for machine learning. It used for some high-level reliability for our communications, but it's not designed for the data analytics, not designed for the machine learning. So we need to rethink and how to build to enable the closed-loop optimization, leveraging such kind of big data and also the machine learning technologies. And regarding algorithm perspective, as we all know, we already had some very useful and traditional optimization theories for the wireless network. So they don't need some stringent requirements for this algorithm, but for wireless systems, since we have high requirements for the reliability, so we need more robust algorithm, and how to deal with such kind of problems is also the big challenges we are facing. And based on the preliminary research, we do see that significant gains of machine learning only expected in complex scenarios, which is hard to model. So for the algorithm part, we need to find which scenarios is suitable for the machine learning algorithm and what kind of machine learning is suitable for that, and how to improve the robustness of the algorithm. Next part, we would like to share some views on the machine learning enabled service innovation and formalization. So based on the wireless big data and machine learning algorithm, we think we will make the network more customized and more smart and more open. So here we will provide the personalized experience for the users with real-time QE guarantee and also personalized content and service caching and access technologies. And for a smart network, it will help to promote the business and marketing while leveraging the network data, so we can improve the network operation maintenance efficiency, energy and resource efficiency. And for the open part, we will help to open the network, or for example, to make some more value-added services to our customer, for example, location, and we can also evaluate the service performance to provide to our customers. So all these kind of capabilities are based on large amount of data in our network. As I mentioned before, we have signaling data, network management data, terminal data, user information, traffic information, parameter, and also the configuration information in all this work. So based on all this data, we use machine learning, the model training, and also some other useful mathematic tools to help us to identify network problems and also provide some predictable behavior of the network. So next part, I would like to share more views on how to bring AI intelligence, the artificial intelligence and machine learning to radio access network. So as we all know, the classic, so here we do think machine learning and AI AI will provide some very good capabilities for our network. So the first part is about sensing. So we have multi-dimensional data, as I mentioned. We have the cross-layer context info, radio environment map. And based on the sensing of this data, we can do some very useful prediction. For example, the user behavior, trajectory, location, and the traffic fluctuation and service type identification. Based on the sensing and processing, we can make some further intelligent decision making. So the machine learning, deep learning, technologies can be used to do some offline model training and also online decision making. So for the use case perspective, we do think now we had a lot of usage of AI machine learning already in the operation management plan, but that is almost static or semi-static. So for example, we have network planning, network deployment, network operation maintenance. So going forward, we do think it's also quite important to introduce AI machine learning into more real-time domain, that is control and data plan. So we can do some optimization also for the protocol stack and signaling, and also use AI machine learning to improve the efficiency of the traditional radio resource management, and also to improve the physical layer performance. So a lot of studies are being doing in both academic and also the industry partners. Okay, so next page, I would like to share more details on the use cases and how AI machine learning will empower the radio access network optimization. So for this page, we try to classify the use cases based on the time availability, data availability on the time and resource domain. So generally, we categorized these use cases into three categories. So the first one is more about the management plan, is usually non-real time. So the time validity for such kind of optimization is usually days or even months. And the green part tries to show more near real-time control and user plan optimization. And for the blue part is more about the real-time optimization for the multi-user scheduling, link adaptation, and the AI-empowered physical layer design, even for the RF, the AI DPD optimization. And for the non-real-time part, we have the network plan deployment optimization, network anomaly detection, the radio frequency parameter optimization, and also network energy saving. And for the near real time, we have most of the radio resource management algorithm, for example, the slice resource management, acute QE optimization, load balancing, interference management, and also mobility management. So based on these three categories, our understanding is that the data is really easy to obtain for the management plan, and the optimization time granularity is also larger. So it is more mature for now for the management plan. So it's more like some commercialized algorithm are already deployed in our real network. And going forward, the near real time part is more like testing and trial, is not so mature. And going down, we also have the real time part is more like the research phases. We all know there's a lot of research on the mic layer and also physical layer on bringing AI machine learning into the networks. And with time granularity becomes smaller and smaller, and it becomes more challenging for the researchers. Okay, so this page we would like to share also the use cases, but it is from another perspective, more about how the value driven. So from the value point of view, we have categorized these user scenarios into three categories also. So first part is our service QE assurance. So for this part, the main purpose is to provide customized network capabilities and service assurance for our, especially for the diversified verticals. The second category is about safety enhancement, that is the communication part enhancement. Is more to improve network resource and energy efficiency, while the capability exposure is provide value-added services for our customers. As for the QE assurance, we have the QE or SLA prediction assurance. And for the safety enhancement, we have the use cases, as I mentioned before. It's more about how to improve the communication experience for the end users. While for the wireless capability exposure, we can expose some wireless positioning information and radio bandwidth prediction to empower the applications to make some adjustment for the services. And based on all these use cases, there are also three domains of the key technologies have been identified. The first part is about RAN data collection. So the layer 1, layer 2 measurement data, MDT, and signal data needs to be standardized so that we can enable all these kinds of innovation in for the AI machine learning algorithms. And here, when we're talking about the RAN data collection, we need also to consider efficiency here. So the mechanism may also need some optimization. For example, some use case-driven data subscription is desired. And for the second technology domain, we need to consider about the RAN data analytics and the machine learning functional framework. So this part will include the data collection, the training, inference, decision execution. So ITOT, ML, 5G task focus group has done a lot of good work on this domain. The next part is more about the architecture, interface, and procedures. We need to consider whether the centralized or distributed architecture we need to do and how to do the model distribution and update. It's quite different from traditional communication network. Okay, so with all these challenges and opportunities, we would also like to share some views on the 5G, beyond the 5G vision from CC view. So for the 5G plus, so beyond 5G, we think the network will continue to evolve towards the deep CT, IT, DT convergence. It will be more open and smart. So in the past 10 years, actually, we are more talking about the CT and IT convergence. And now with AI machine learning technologies, we're more talking about CT, IT, DT with native AI. So we also call it DICT, deep convergence. So it will, with such kind of deep convergence, will enable more smart network. It will be more intent aware with embedded intelligence, and big data analytics and AI machine learning will be native components of the network. And with all this smart, we think the network needs to be more open also. So we need to introduce more open interface and API, and also the open source activities will help to build more healthy and more innovative ecosystem for our 5G network. So here we also shared some picture on the overall picture. We are considering since 2017. So as we mentioned with native AI, that means for all domains of network needs to consider to bring AI into the network. So for the core network, the upper layer of this picture that we have the core network. So we had to introduce a network data analytics function, which is designed to enable the data analytics and AI machine learning for the core network. And also for the management plan, we will have the big data analytics and machine learning functions also. And regarding the radio access network, we should also introduce the radio data analytics part to make sure that we can have the different domain intelligence, as well as we need some collaboration between the three different domains. And here is some paper that we are doing before 2017. So next part, beyond the use cases and key technologies and visions, we would also like to share some standardization progress or activities in the industry. Okay, so for the research part, we had initiated wireless AI Alliance in 2017, which is leading by China Mobile, Alibaba, and some universities in China, which is focusing on working on how to bring AI machine learning into the radio access network. And we also had some support from some forums, for example, the Wireless World Research Forum and the Future Mobile Communication Forum in China. And there are also some academic activities in IEEE also. They have the network intelligence and machine learning for communications, emerging technology initiatives. And for the standardization part, we don't know ITOT is needing the work on the AI machine learning for 5G and future network. And also in 3GPP, we had some study items on bringing AI, big data analytics into the wireless network also. So in RAN 3, SA2, SA5, we had different kinds of study items and work items working on this. And also in ORAN, which is organization leading by the operators, they also had some work on the radio intelligence controller in the radio access network. And for ATSI, we have the ENI, and the different working groups working on the automation of the network. From an open source perspective, we have the NIX Foundation had initiated the NIX Foundation AI, which works a lot on the AI machine learning open sources. There's a whole ecosystem for the different parts of the AI machine learning pipeline. And we also had the ORAN, ONAP, Oculus, ADMIC, and PND. The different lots of projects are working on this quite hot topics now. So this page, I would like to share some overview of the standards and open source for the AI for wireless network. So as I mentioned before in 3GPP, there are some studies in RAN 3, SA2, and SA5. So for example, in the radio access network, we had some study item on the RAN-centric data collection utilization for the NR network. And there's also some study for the enablers for network conversion in the core network, and also other autonomous network levels study in ETSI and 3GPP. And for machine learning 5G focus group in 5G, the main purpose is to study the machine learning for future networks, including interface, network architecture, protocol, algorithm, and data formats. There are a lot of recommendations that are already published. So it is quite helpful for the industry to understand more about the overall framework of how to bring machine learning into architecture, provide very good guidance for the further detail standardization work in 3GPP and other standardization organizations. Okay, so for the ORAN part, it's more focused on the radio access network. So we had introduced a radio intelligence controller into the NR network. So this work is leading by SMCC, AT&T, and DT. Will enable the closed loop automation optimization of RAN elements resource, making more elegant and more granular and more flexible. And also the embedding intelligence will be introduced in RAN to improve the traditional closed loop control functionalities of the 5G network. So the open source part, as mentioned, there are a lot of work around the AI data collection, network embedded AI, and network automation. So here we would like to summarize the key issues on the AI machine learning in this SDOs and open source community. So here is a list for the key issues they are working on. The first part is the use cases and requirements. The second is the impact on the system architecture. And also some hot technology has been discussed. For example, the intent policy, network intelligence level, and the machine learning data input output. the interface for data collection, how to do network configuration control, and also the how to define the information model and data model, and to make it more efficiency, how to do the AI machine learning, AI model transfer, and how to do the AI machine learning model functionality orchestration. So here is some kind of summary for the key issues being studied in the industry. Next part, I will share more recent research progress from China Mobile's perspective. So first is about the machine learning for multi-rate energy saving. So in our network, we have a lot of different wireless systems. For example, we have the 2G, 3G, 4G, and now we have the 5G. So there are a lot of over coverage of such kind of systems. So we need to consider how to fully utilize different systems to make it more energy effective. So by the full integration of the big data platform and take advantage of multi-dimensional data from our network. So we have developed a system to find the no traffic cells, and so that we can deactivate or activate them appropriately without any performance data, without any loss of the network performance. So here is the overview of all the systems. So here is different kinds of data collection equipment in our network. So we will collect all this data into our platform. So in our platform, we will use a machine learning algorithm to predict the traffic flows. So a lot of data have been collected from a network, for example, the measurement data, configuration data. So it's real-time performance data every 15 minutes. And after that, we use a machine learning to forecast the user trajectory and service profile. And in the third phase, we also introduce some signaling data so that we can provide the user location service profile. Okay, so this system has already been deployed in our commercial network. So for more than 970,000 cells across 19 provinces in China. The average annual electricity saving will be more than 200 million kWh each year. So the next use case is how machine learning can be used to improve the radio resource utilization. So the background here is that in CMCC's 4G network, we have a lot of different bands. So the load balancing among the multi-frequency, multi-layer cells has become important and quite challenging issue. So we need to improve the resource utilization. So we have the D1, D2, D3, FDD1, 1018 bands, and also F1, F2, FDD 900. So how to balance the traffic in such in a lot of bands will be quite challenging issue here. So here, the solution here is to optimize the network parameters of the cell handover reselection among the capacity layer, the coverage layer, and enhancing the coverage layer. So the network traffic load can be evenly distributed according to the cell traffic capacity and network resource utilization, so that the network resource utilization can be optimized. So here is a general procedure of how to do such kind of optimization. First, we will collect the data and do some cleaning and analyzation and feature selection. After, we will cluster the user distribution of the cells to find the features of each kind of the cells. And based on that, we will generating the solution, use some static training results for different cluster cells. And after that, we will do some parameter optimization and searching based on the optimization algorithms. With the machine learning models, we will continue to monitor the data in the network to revise the solution dynamically using some field test data. And this table shared some results and in performance gain in our commercial network. Next part, so the high quality data is actually the basis for study. So here we listed some different kinds of data in the network we are using. In this case, we have the site and location data, and the measurement data, and also the configuration data, the performance data. And all this data will be associated to generate some data set for the model training. Okay, so the next use case is about anomaly detection and root cause analysis in our commercial network. So this is a 3-phase study from 2018. We had done some anomaly detection model validation, use some offline data of the 4G network from CMCC, and then last year we had some further root cause analysis on CMCC Shanxi province for the both 4G and 5G network. And 2 anomaly detection use cases being further identified. The first is about the 4G and 5G network current operation, and the second is about the KQI anomalies, that is key quality indicator anomalies, root cause analysis, and relevant, the key performance indicator anomaly detection. And in this year, we are trying to do some online trial on the Shanxi province. So some post-processing and root cause analysis automation for the KQI and KPI anomalies will be done in this year. So here is some preliminary results for the radio access network anomaly, which is quite sensitive to the user experience quality degradation. So based on this, we had analyzed a lot of key performance parameters in our network. For example, there's some RC clashing problem, and also latency problem and user throughput problem. So compared to the anomaly detection top 15 cells for radio access anomaly, the traditional trouble ticket of the radio access network shows 78% missing detection, and as an improper threshold setting is being done, so the user experience will degradation. And with the anomaly detection using the AI machine learning algorithm, will be the solution. The results will be more accurate and will provide more valuable guidance for our maintenance engineers. Okay, so next problem is about KQI problem, anomal RAN KPI location. So here, for the service for the bad service quality KQI problem, the anomaly detection can automatically provide the abnormal KPIs parameters for each cell. So the mapping analysis between the KQI problem and KPI is helpful to solve the KQI problem. Here we have listed some most abnormal KPIs in the network. For example, we have handover problem, we have the ERAP drop rate, and also, so based on this, we had a root cause for this KPI. So the human record is that is over coverage, and based on the comparisons, it will provide some very useful guidance for network engineers. Okay, so the next use case is about machine learning powered QE cross-layer optimization. So here, a lot of different machine learning models can be utilized in this work. So first is about application identification. So with the AI machine learning models, we can identify application types without the DPI, that's a deep packet inception. And also we can provide real-time KQI or QE prediction. And the other thing we want to mention is that we can also expose some second level or even 100 millisecond level of radio access network status to the applications for the service optimization. And based on all this predicted KQI, QE, we may also further derive some optimal radio resource management to enforce a closed loop quality of experience guarantee from the radio access network. So here is the overall flow for these use cases. And we can see we need different kinds of AI engine to be deployed in our network to enable the whole solution. In the right side, we provide some preliminary results for the AI machine learning models that are used. The first one is about application identification. So based on the study, we can achieve more than 95% accuracy for 11 typical applications. And the network is a 17-layer CNN network. And also we had done some field trial with our partners. For example, with ZTE, we had verified the AI-enabled high-quality VOD streaming, KQI evaluation, and accused assurance in the 4G trial network in 2018 and 2019. And with Nokia, we had done some AI-enabled cloud VR QE evaluation, Q's guarantee in the 5G trial network last year. And we also made some in-house. We also made some in-house in CMCC. There is a POC, proof of concept of the AI-powered KQI prediction and Q's optimization. So the main purpose is to predict the stalling probabilities for the video streaming per 100 milliseconds. So we got a lot of measurement data from the radio access network, for example, UE channel status, the cell load, the MAC data rate. And with all this data, we had to AI machine learning model training to predict the stalling probability based on the network status. So we can achieve almost 90% accuracy. So with all this prediction, we will also enable some enhanced radio resource management and scheduling algorithms. So based on this verification, we can say that the KQI is significantly improved based on the AI machine learning solutions. The next is also some research work on how to use reinforcement learning for network slicing and resource optimization, since I think I don't have quite enough time for today, so maybe I will quickly go through this. Okay, so going to more real-time use cases, we also done some research work with our partners on that AI-powered beam optimization and link adaptation. So for the beam optimization for the master MIMO is quite hot topic in the research area also. So in 2018, we had done some research work together with ZTE in Guangdong province in China. We had done some master MIMO beam pattern optimization in our commercial network. So the field test, we had done the field test for 3 months. The obvious gains of user number throughput can be observed based on our machine learning algorithms. And another exploration we have done is about smart link adaptation. It's more about the mic layer with Huawei in Shanghai. So we are using the machine learning model to predict the packet error rate or throughput for the users with all these KQI, rank, and connect CSI, which is more like physical layer measurement results. So based on this machine learning algorithm, we can achieve up to 10 or 15% gains in the experimental network in 2018, and some real network data collection in Zhejiang commercial network, and also do some offline AI machine learning training and analysis. Okay, so the last one I think is a radial fingerprint based on load balancing. We also have some demos shown in MWC 2019. Okay, so here the main concept is to construct a radial fingerprint of the network based on the measurement data from a network. So we can have a virtual grid of the network, and based on that we can do some predictions for the qualities of the network. With that, we can do some real-time optimizations for our network. So here is the basic results we have got in our lab test. So the radial fingerprint-based algorithm can enable more valid measurement reports in a timely manner and leads to faster load balancing, and more than 40% high load duration reduction can be achieved in our lab test. And now we are doing some field tests in Fujian province. Okay, so last part, we also, with all these use cases we have shared, we also had done some preliminary research work on the data part for the wireless network. And here is some preliminary thoughts on the considerations for the open data set for wireless network. So here, as we know, we have lots of kinds of data on network, and we just think it's very important to have some open data set for the wireless network, so that it can help to fasten the research work in your wireless domain. As well know, for the NLP and image processing, they are very famous and well-defined open data set. So the algorithm will developed a lot of innovation in that areas. So we think for wireless data network, we also need such kind of open data set. So we had done some analysis for what kind of data that we can consider, for example, application, user level, network level data, file level data. Based on this, we can develop some key capabilities, some basic capabilities for AI machine learning model, for example, the QE prediction, mobility pattern prediction, and cell traffic prediction, user distributed prediction. All this will be the key pillars for the wireless network applications. Okay, so next part, I would also like to share some recent work where we are doing together with Huawei. So we had the first wireless big data competition in 2020. We have two topics for this competition. The first one is the RAN aware user experience prediction. So it will predict video stalling based on RAN real-time data. The second topic is about intelligent RAN UE positioning based on the RAN measurement data. So more than 70 teams and 120 teams have joined this competition. Okay, so last page, I will want to share some lessons learned and challenges for the future work. So based on all this research, we do think AI is just a tool, and it's more suitable for the large dimensions and dynamic and complex problems in the radio access network. And both data-driven and model-driven intelligence algorithms are expected for the 5G radio access network. And performance gains versus computation complexity needs to be continuously studied in the future network. And the wireless AI machine learning model generalization is extremely hard due to the dynamic network environment and how to solve this problem. Whether we can use a transfer learning, is it a good solution for this? I think further study are also expected. And since the wireless network is quite distributed network, so edge intelligence with distributed reliable machine learning algorithm are desperately desired. So what's the solution for that? Federated learning or collective learning, and how to do that, how to enable that in the 5G wireless network. The next thing is, as I mentioned, the wireless open data sets are desperately needed to set up the algorithm benchmarks and also boost their machine learning algorithm for wireless domains. Okay, that's all for today's sharing. I think I'm over time. I apologize for that.
Thank you so much for the wonderful presentation. Now we have some questions now in the Q&A window. So I would like to ask Vishnu to take over, moderate the Q&A session.
Thanks, Thomas, and thank you so much. It is late evening in China, but you have taken the time to come and talk to us about this work. It is, of course, a pleasure to talk to Chi. Chi is our longtime colleague. She is the main editor for one of our recommendations, ITUT Y.3174. So thank you so much for coming and talking to us. The first question is actually related to what you have here. Actually, it is my favorite question as well, about the trade-offs. So you mentioned about trade-offs. Alex is asking the same question, that you know, you mentioned federated learning. You in some of your slides you did talk about training, and there are of course computation needs for training. So have you done some studies regarding this kind of trade-off, and what is your opinion? What are the costs, and what are the benefits that you see, and what kind of considerations that you see from your studies, please?
Yeah, thanks, Vishnu. And I think that's really a good question. Yeah, and it's really quite an important topic for the wireless network. As we all know, the wireless network is most computation limited, and also the bandwidth for the data transfer is also limited. So for our research work, actually, we had studied some part of this problem, but we are more like test and trial. So actually, we don't find good way to do that. That's why we also pose this question here, and hopefully we can work together with our partners to do more good work and have more things to share with you.
Thanks, G. Yes, I was typing the answer. Yes, thank you so much. We understand. Actually, that brings us to the next question. You mentioned about open data sets. You mentioned about China Mobile's challenge initiative. You already discussed two of the problem statements. Yes. You know that ITU is already doing global challenge. So this kind of open data sets are desperately needed, to use your own words. What is the way to format those data sets? I mean, we discussed about this in the context of 3174 also, that the structure of the data, it can be structured or unstructured, but the format of the data sets has to be well known, and it has to be known beforehand. What is the way, and could you give us your thoughts on how to set up these wireless open data sets, and the structure of the data, format of the data? Also considering that operators don't share data generally. I mean, generally they don't share data. What are your thoughts on this, please?
Thanks, Vishnu. So regarding the data structures, as I shown in this, I think it's good to have a good structure. For example, probably we can categorize the data into different layer data. We have the application layer, user related, network data, and file data. So based on this, actually, in our management system, we have some well-defined data model, and that part is well known by the industry and well standardized in Switch VPN or other standardization organization. I think that's a good start. We can reuse some well-defined data models, and that is also the proposal in the Y.3104, right? So it's much easier for us to start all this work. And regarding but my understanding, all this data are just raw data, right? That is not to solve some particular machine learning algorithms. So based on this data, it's good to have some specific topic, right? What kind of the basic, the key issue problems we need to solve in the wireless domain. We can form some key capabilities, AI capabilities in our network. That's why we had the second level. Yeah, we can consider what kind of AI machine learning models will be quite useful in the network. Then probably we can consider the QE prediction problem or the mobility pattern prediction problem. So based on all these problems, we can set up the data sets for this problem. It's quite similar to the image processing, right? They just do the single job, that is to recognize or identify what kind of thing it is. It's much easier to start. That's also our understanding. So based on that, in this year, we had the CMCC and the Huawei competition. It's almost the same philosophy here. So we had two specific topics here. For example, the video stalling problem. Then we had clearly defined the potential input feature and also the useful output labels for this topic. And then we will share this data in our platform to the team so that they can access. So that's my understanding on the first question. And second one, yes, it's really hard to open some data even for the operators. There's a lot of security issues, right? And yeah, so but to make it the industry really go fast and make it AI machine learning to really useful in AI machine learning, we still think it's important. So I think competition is a good way to do that. So we have limited access for the participants that is not fully open. So the data is still kept in our internal platform. So that is not truly or fully open data set. And actually, as I talked to Vishnu, so earlier this year, we also proposed this competition for the AI challenge, ITOT AI challenge. But since a lot of teams are competed for this in China, so actually we failed. So that's why we need to do another competition here, and hopefully next year we can do some joint work on this.
Thank you so much, Chi. Could you go to slide 24? 24, I think, yeah, there is a question. I think, yeah. Yes. So you did talk about RF fingerprint and analysis of that. There is a question, I think Alex is asking for radio environment map, spectrum sensing. I think it is quite related to this one. I want to ask you, or rather he's asking what is the use case. I am trying to map this to this. You are, in this slide, you are talking about proactive load balancing. Can I ask you, who is sensing the data here? Is it the UE based or is it some other sensor? And where is the output from the inference going? Is it going to the, it is going to the CUDU, is that true? As well as to the UE, looks like. Could you explain this input and output and what kind of use case this is? Thank you.
Okay, thank you. So first, the data is collected from the UE side. There is no sensor in the network. It's a typical 4G network. So first, the UE will measure the quality, the coverage quality of the network. Then it will report the measurement report. For example, the RSRP, RSRQ, to the AI model training functionalities in the network. For example, it can be the management system of the network. So with all this data, we can do the model training. And here, so the input for the model is measurement report of the intra-frequency cells, RSRP and RSRQ. So based on this intra-cell frequency measurement, we would like to predict the inter-frequency measurement report. Since in the 4G network, if we do the inter-frequency measurement, there will be some gap mechanism. It will lose the capacity of the network. It will also cause some delay. So we need to predict the inter-frequency measurement results first, and then we can choose the appropriate cell and UE pairs so that to balance the network. For example, the cell A is fully loaded, but cell B is still low load. So that we can choose. We need to first measure the quality of the user for both the cells, and if it is good in cell B, and then we can move the user A to cell B. So here, the machine learning model is just to predict the singular quality of the labor cell. And with this prediction, we can choose the most appropriate UE and labor cell, so the UE can do the handover. that's the whole procedure here. Hopefully, it clarifies your question.
Thank you, thank you. So do you use it for interference management, or is it just load balancing?
And for now, it's just load balancing, but it can be further used in other scenarios, as you mentioned, interfrequency management, and also the carrier aggregation optimization, and even for the dual connectivity in the 5G network.
Okay. Yes. Thank you. Thank you, Anchi. I think that's the questions that we had. And once again, thank you for staying late, for answering our questions very patiently and taking us through the slides and the scenarios which Mobile has studied. We look forward to working with you again next challenge. Maybe we can do it together. And thank you once again.